Hello students, so let us continue to discuss the module 4. We have discussed about work done, then we have discussed about conservative, non-conservative, we have discussed about some examples, right? So today we'll go further into that. We have also covered work energy theorem and energy conservation. So let us now discuss about power. What is power? Power, it is the rate at which energy is used. Okay, so if you take power is rate of doing work, dW by dt. Now what is work? Work is equal to displacement force into, right? It is the dot product of force and displacement. You can also write, if it is like a total work by total time interval, you can write. So work done will become force dot displacement, this is delta R, and this is the time, right? It will become force dot delta R by T is velocity. So force dot velocity, right? We can write like this. And if there is no other forces, only conservative forces are applied, then work is change of kinetic energy. Right? So it is also equal to rate of change of kinetic energy, right? Okay, this is like the instantaneous power. Right? So you may also write power as the work done is small work done by small t. Now here work done you have to write as force into small displacement that has happened. Assuming force is constant, then force will come out, right? So this is force into small displacement dx by dt. So that is what is velocity, force into velocity. Okay, and of course it's a dot product, so you may write this as dot product, or this dx can be written as dr in general, dr factor. So it's dot product of force and velocity, right? This is instantaneous. Average means over total interval of time, work done total. This is like a average if you take. That also we can write, but this is generally instantaneous. Okay, force dot velocity. Okay, then next now let us see some applications of graphs. So first graph that can come is force versus x graph. So what is the area under this graph between two positions x1 and x2, right? What will be this area? Suppose if they ask, what will be this area? Okay, so the area under this graph, it is the integration, right? So integration of f dx, that's the area. This is nothing but the work done by the force. Okay, area under this graph will give area under fx graph gives work done by force. Also, it is important to note that if the graph is between power versus time graph, okay, what does that represent? Again, we can think about in the same manner. So integration of power time, what is the area under this graph? This area is nothing but, because power is equal to dw by dt, this is nothing but the total work done, which can also be written as change of kinetic energy. Okay, right, that's important. Two graphs we have discussed. Then there is one more graph which is also important. Sometimes questions come directly based on that. The third graph is power x graph, px graph. What does the area under this graph between two positions x1 x2 represent? Let us think about it. So this area, let's integration of p dx, that's the area. What does this area indicate? P dx. So power can be written as force into velocity, right? Force into velocity into dx. Now we can write force as mass into acceleration, right? Mass into acceleration into dx, right? Okay. Now and this is v is also there, right? Now we can also write acceleration can be written as v dv by dx, right? Acceleration, and this is v dx. So from here dx will get cancelled out. So what we will get is mass is constant, take out, this is v square dv, and let's say velocity is going from u to v, initial to final. So this integration will give us m v cube by 3, and you have to put upper limit and lower limit. So this area of p dx, right, this area is giving us m by 3 or m v cube by 3. Let's take m by 3 common, so it is v cube minus u cube. This is an important concept, because some questions they will give this area to calculate. Okay, right. So these are some graphical concepts. Then what next? Let's move to the concept of equilibrium. Equilibrium. What is meant by equilibrium? Equilibrium means, here we are talking about translational equilibrium. So the net force acting on the body is equal to 0, right? That's what it is, equilibrium. Now coming here to take the point, what are the different types of equilibrium? So one is called stable equilibrium, second is called unstable equilibrium, and third is called neutral equilibrium. There are three types of equilibrium. So what are stable, unstable and neutral, we should know. So stable equilibrium means the potential energy of the body is minimum, right? Potential energy is minimum. And what is unstable equilibrium means? Unstable equilibrium means potential energy is maximum. And what is neutral equilibrium? Potential energy is equal to 0 or constant, not 0 necessarily. Potential energy is just constant. Okay, so here we should note that the differentiation of potential energy with respect to x, let us say, is equal to 0. Here also potential energy with respect to x is equal to 0, but here also potential energy differentiation with respect to x is 0 because it's constant. Okay, so net force is defined. That is what you have to understand. Here potential energy we are going to write as U. Let us use potential energy and say U. This is the symbol which is used generally for potential energy. So the force, conservative force, is written as minus du by dx. Okay, but of course force can also be written in terms of 3 dimensions. Force can be written as minus dou u by dou x I cap minus dou u by dou y j cap minus dou u by dou z k cap. This is force vector. And if you are taking in terms of symbol, so there is a del vector into u. This is what is the conservative force. So conservative force, last time we discussed, this is how conservative force can be written. So for conservative force or conservative system, potential energy is defined. Potential energy is defined only for conservative system. Okay, so that's what it is. Equilibrium, different types of equilibrium. You want to understand with one example. let us take this. So if you consider like this, let's say body is lying here at the bottom most of this, then there can be a body which is lying here at the top most of this, and there can be a body which is lying at some height which is constant, right? So in all these cases you see here the potential energy at the bottom, so potential energy is minimum. Of course force is also zero net force, okay, so potential energy is minimum, and forces, of course mg will be force, and from the contact normal and mg are equal, so net force is 0 here. In this case also mg and normal can balance, so here also net force is 0, but we need to note that the potential energy in this case is maximum, right? And here if you see this case, this is of course balanced because normal from the contact surface and mg on the body, this is balanced, so here also net force is 0, right? But in this case potential energy is constant. So that's the case of stable equilibrium, unstable equilibrium, and this is neutral equilibrium. So if you disturb the body from the stable equilibrium, let us say you bring the body here or here, it will always try to go to the mean position. Here if you disturb this side or this side little bit, it will go away from the mean position. Here if you disturb anywhere, it will remain there itself, okay, so it will remain there wherever you keep it. That's the concept of stable, unstable and neutral equilibrium. So if you see the graph here of potential energy, so as we discussed, force is minus du by, let us say, one dimensional dx, okay. So potential energy is minimum or maximum, so for that what we should have, du by dx has to be 0, du by dx has to be 0, differentiation, right? That's why force becomes 0. That's why it comes under equilibrium, right? Force means the net force here, okay. And now if we want double differentiation, so what will happen in double differentiation? That means df by dx, that will give minus d square u by dx square. Okay, so the shape of the graph, if you see like this shape, you know, this is going to be positive. Positive means the double differentiation, let's say this is potential energy graph, so double differentiation is positive, okay. This is potential energy versus x graph. Same way, suppose this is potential energy versus x graph, and this is a concave convex shape. So here double differentiation is d square u by dx square is going to be negative for this, right? So when d square u by dx square is positive, the df by dx is going to be negative, okay. So if you draw force versus x graph, slope will be negative, okay, negative slope. Similarly here in this case this is negative, so if this is negative, d square u by dx square, then negative become positive, force will be having a positive slope. So that's why this is important to know. And let us say force is maximum or minimum, and so df by dx is equal to 0, right? So if df by dx is 0, then force is either maximum or minimum. So we can plot the force versus x graph also for this case, okay, right? So these are some of the important graphical concepts in this. So we have covered I think this chapter, then we will be taking up further problems in this. Thank you for your attention.